this video, I'm going to show you how to set up your HEC-HMS model from scratch, delineate your watershed, figure out your subbasin, characterize all the parameters in your subbasin, and eventually do a simple hydrologic modeling for different watersheds and different subbasins. But before that, I'm going to show you the data that I have. I have created a folder, HMS demo, and I have two subfolders inside that. One is outlet, in which I have the main outlet of the watershed that I want to model. And the other one is a sample digital elevation model. And I have a digital elevation model that I want to delineate within HEC-HMS. If you want to follow along with me, I have included a link in the description section of the video, or if you are coming from my website, there should be a link in my website that you can download the data that I have over here. Okay, so let's get started from the beginning. First, we need to start a new project in HEC-HMS. And I'm going to click on this button over here and start a new project. I'm going to call it HEC-HMS demo. And you can write a description. It's a good practice to write a description for each project that you're creating. Because this is a test, I'm not going to write a description. You can change the location that you want the project to be saved, and obviously you can choose the unit system. I'm going to do the US customary system of units, and then I'm going to create that project. All right, so right over here you can see that the notes, the errors, and the warnings are going to show up over here. So if there's anything in red or yellow, you want to pay attention to fix the model. All right, so you can see that the project is created over here, and it tells you the directory that your project is saved. Okay, now we are going to start by defining different characteristics of our hydrologic model. So when you click on this components over here, we are going to go one by one and create characteristics of our basin and our hydrologic model. I'm going to start with Basin Model Manager. In order to do hydrologic modeling, you need to have a watershed or a basin. And we want to manage that basin. So I'm going to click on that. And then you need to create a new basin or a new watershed, right? Because I'm going to create only one basin, so I'm going to remove this one after that. But if you have multiple watersheds or multiple basins that you want to model, it's a good practice to have them numbered. Basin 1, 2, 3, so on and so forth. So I'm going to create that and then close this window. You can see that once I create the basin, a basin model will pop up. Since I created only one basin, it's over here. If you click on it, it will give you some basic information about that basin, what you want to model, what you don't want to model. All right. Since we are going to do watershed delineation within HEC-HMS and not in any GIS software, we need to add a terrain data or digital elevation model. Again, if you click on components and then go under Terrain Data Manager, it will ask you to add your digital elevation model. And I'm going to create a new one, and I'm going to change this name to digital elevation model. If you have multiple digital elevation models, it's a good practice again to have them numbered 1, 2, 3, so on and so forth. Next, and then I need to find the file name and the location of that. This is very important. The vertical units is very important. I downloaded this digital elevation model from USGS, United States Geological Survey. I know that the vertical units is in meters, so the elevations are in meters. If your elevation is not in meters, you need to change that as well. All right, I'm going to open this and go to the folder that I have created, and I have my sample digital elevation model over here. Notice that it's a tiff.tif file. I'm going to select it and then click Finish. Okay, once I do that, again, you will see that the folder pops up over here that contains the digital elevation model for me. All right, now we want to connect this digital elevation model to the basin that we have. So if you click on the basin, and if you go to this terrain data, I'm going to expand it and connect the digital elevation model to my basin model. And now right now nothing shows up over here, right? But if you want it to show up, you need to click on DEM. So you will see that you get a message. You might not get this message. If your digital elevation model has a coordinate system, you're not going to get this. When I was processing, or I should say pre-processing my digital elevation model, I didn't specify any projected coordinate system, and now this message is telling me that my digital elevation model doesn't have any projected coordinate system. If you want to select a projected coordinate system, you can select it. If your watershed is not too big, that's not going to cause any problems in your hydrologic modeling. But it's a good practice to have a coordinate system either specified in your GIS or here. I'm going to skip it for now. And you can see that the digital elevation model shows right over here. Sometimes if your DEM is a little bit large, some part of your DEM is going to be hidden. Right now you can see that it's artificially has cut my digital elevation model using this straight line. But I know that that's not the case. That's not a problem. The data is saved in HEC-HMS. It's just a bug in showing your DEM when it's large. All right. So now we have our digital elevation model. We need to delineate the watershed to figure out the number of subbasins that we want to do hydrologic modeling for. In order to do that, we need to go through the GIS module. But before I do that, I want to show you how you can modify this digital elevation model. Under View tab, you can see the map layers that are going to show up over here. So if I uncheck terrain, you can see that it disappears and then appears again. If you click on Draw Properties, you can change the properties of this digital elevation model. For example, you can classify into different elevation bands, or you can change the color scheme of your map. For example, let's see if we can find a good digital elevation model, or we can find a good color scheme for our map over here. I'm going to select maybe this one, yeah, and then apply, and then click OK. You can see that the lower elevation are lighter shades and white, and the darker or higher elevation are darker green. Okay. All right, so now we are going to delineate our watershed. I'm going to click on GIS over here, and one by one, step by step, I'm going to start from pre-processing sinks all the way to delineate elements and so on and so forth. What is pre-processing sinks? Especially in northern United States, there are many isolated depressions, wetlands, so on and so forth that interrupts the network, the river network or the dendritic river network. By doing this, you are artificially removing these sinks from your digital elevation model. So I'm going to pre-process the sink. You can see that these are all the sinks that the model finds, the GIS model finds, and then I'm going to go and pre-process my drainage area. You can see that now I have a nice dendritic system of rivers connected to each other. This is the flow accumulation. In other words, when you hover over different cells, it will tell you the number of cells that are contributing to that specific cell. Okay, and then under GIS, I'm going to identify streams. When you want to identify streams, it asks you about the effective area for stream definition. The effective area tells you how big you want your sub-watersheds to be. If you want larger sub-watersheds, obviously you need to increase your effective area as well. So this means that more area is contributing to those streams. If you want teeny tiny watersheds, you need to decrease your stream definition. It gives you some suggestions based on the topography. I'm going to change this for this study area. I'm going to use the effective areas of 4 square miles and click OK. And you can see now it defines some streams for me. The darker shades of red, or I should say maybe brown, represents downstream of the river where the flow is higher. And the lighter shades of yellow, I should say, represents less flow or smaller streams, less flow into the streams. All right, so these are my streams. Now if I go to GIS, I can see that after identify streams, next is breaking points manager. Breaking points in HEC-HMS is outlet of your watershed. Where do you want the outlet to be? So if you click on it, it asks you to input an outlet for your stream. I do have a shapefile. I showed you right over here that I have shapefile saved in the outlet. I am going to import that shapefile, And make sure that the snap breaking points to identify stream is on, and then select the stream that you have. It's already knows where to go for me. For you, you need to navigate to outlets. I have 2 outlets over here. I'm going to select the main outlet and then open and import. So you can see that I have an outlet or breaking point right over here, which is the upstream of my watershed. All right. Go back to the GIS tab. Next is delineate elements. So if you delineate elements, it asks you, what do you prefer to be the prefix for subbasin? You can write subbasin, or in my case, subbase S represents subbasin, R represents reach, junction is where the subbasins could be connected to each other. I'm going to show the junctions, and the prefix for that would be J, and then delineate the watershed. After a couple of seconds, you can see that there are some icons on my map. This represents a watershed over here, S1, S2, and S3. There is a reach. This blue line is my reach, or essentially the stream. This is a junction over here, and right over my outlet, there is a sink point, which represents my outlet. To make this map a little bit more visible, I'm going to go under View, Map Layer, and turn off the maps that I don't need anymore. For example, I do want to have the icons and reaches and subbasins, but I don't need the breaking point anymore. I don't need the identified streams anymore. What else? I don't need flow accumulation. I don't need flow direction. Sinks I don't need. And then sinks filled I don't need. Let's keep the terrain over here as well. So all of these rasters that you could see over here are saved in the folder in actually right over here in this directory that you have. So later, if you want to import them in GIS and create a nice map, you have access to those rasters as well. Okay, so this is a better view of my study area. You can see as I zoom in and zoom out, it changes the visualization. Again, because my raster is a little bit large, it has some problems visualizing the raster, but at some point it's going to show all of it, and you can see even the colors might change a little bit. Okay, so I'm going to keep it like here. Perfect. This is how you can delineate watershed automatically in HEC-HMS. You could manually input these 3 subbasins, the junction, the reach, and the outlet, using the buttons are over here. You could manually import all of these. You didn't need to do watershed modeling, but the cool thing about automatic delineation is that the watershed characteristics will be automatically imported into your model. What do I mean by that? So if you select your basin, and if you go under Parameters tab, and then go over Characteristics and click on Subbasin, you can see that it gives you a lot of good information about your subbasins. For example, what is the longest flow path length in miles? That information is already for you. You don't need to measure that in GIS anymore. Or what is the average slope of your subbasin? That information is given to you over here. And lots of other good information that helps you in calculating time of concentration and lag time when it comes to different hydrologic processes. So this is the advantage of doing automatic delineation. And you will see how I use that before. Later in the video. Okay, you can see there are some lines added over here. Again, if you want to see what those lines are, go under View, Map Layers. You can see that because I clicked on Characteristics of the subbasins, right now all these shapefiles are also added. I'm going to turn all of them off except for the longest flow path. So you can see the longest flow path right now is represented in my subbasins. Okay. Now, let's talk about watershed characteristics. If you expand your basin, you can see that you have 3 subbasins, S1, S2, and S3. You have 1 junction, J1, right over here, when S2 and S1 are connected to each other. And you have a reach, R1, and your reach is this blue line. That is a stream that connects J1 to your outlet. And also, you have a sink, and the sink is your outlet. If you click on any of these watersheds, you can see that watershed is going to be automatically selected. S2 selected, and if I click over here on S3, it will be selected. Similarly, if you click on the reach, you can see that the reach or the river is selected. So let's say I'm going to click on S1 and then expand S1. You can define different methodologies that you want this sub-watershed to be modeled based off. What do I mean by that? Let's say the loss method right now is the initial phi index method. You can change that to SCS curve number or any other loss method. What is a loss method? Loss method helps you to calculate infiltration and the depth of surface runoff over the sub-basin. You can change your transform method. What's a transform method? That's the method that helps you to calculate unit hydrograph, and then unit hydrograph multiplied by your depth of surface runoff would be your direct runoff hydrograph. Okay, you can change that as well. Right now I have 3 subbasins, so it's easy to click on each subbasin and change it one by one. However, if you have, let's say, 100 subbasins, you don't want to spend time and do this one by one, right? So what's the shortcut over here? If you click on the basin and then go under parameters, and let's say that you want to change the method of loss, calculating surface runoff. Right now, for all of these subbasins, the method is initial and constant. You want to change the method, and it tells you that if you change it, it will change for all subbasins. And that's exactly what we want to do. So yes, and change the method to SCS curve number, not gridded SCS curve number, the normal SCS curve number subbasin based. Okay, change. All right, now if I click on any of these subbasins, let's say subbasin 3, and if I check the loss method, it's already SCS curve number. So this is a way to batch change all these methods within HEC-HMS. Again, I'm going to click on basin. I am going to go under parameters, and this time I'm going to change the transform method from Clark unit hydrograph all the way to SCS unit hydrograph, and then change. Again, I'm going to go under parameters. I'm going to change the base flow method from recession to none. This is an events-based modeling. I am not interested to adding base flow or groundwater flow into my simulation. So I'm going to select none and change. Okay, you can again click on the subbasin and see how the methods have changed over here. If you are doing continuous modeling, you need to add snow method, surface method, and canopy method as well. But because I'm doing event-based design modeling, I don't need to include those in my model. All right, so I'm going to save the model. It's a good practice to save this once in a while. If your model is large, there are times that there are some glitches and you don't want to lose what you have been doing over here. Okay, this is essentially how you change different methods in your subbasins. I'm going to click on the reach as well. And in the reach, you need to select a routing method. What is this routing method? The routing method is how hydrograph is going to be transported from J1 or this junction all the way through the stream to the sink or the outlet method. Right now, the lag method is selected. The lag method is the easiest method and it only requires one time input. And that's the time that it takes, the lag, essentially the lag time, the time that it takes for hydrograph to move from this point all the way to the outlet. If you have physical characteristics of your stream, let's say manning roughness or the shape of your stream, the banks and so on and so forth, you can select other methods as well. A very popular method based on the characteristics is going to be the kinematic wave method. And when you select that and then go to the routing tab, you can see that it asks for the length of the reach, the slope, manning, and lots of other parameters over here. So if you have physical characteristic of your channel, this is a good way of doing reach modeling as well. For this specific stream, I know the lag time, so I am going to select the lag method right over here, which is one of the easiest methods to consider lag in hydrographs as well. Okay, I'm going to save it again, and then just to show you how the junction looks like, it essentially just a junction. Over here, there is not a lot that you can do, but when you have your results, you will be able to see specific results of a combination of these two subbasins that contributes to this junction. Okay. okay? And eventually your sink, again, there's not much that you can change over here. This is only a node that you can extract the results from and see what would be the total hydrograph from these 3 subbasins at the outlet of your watershed, okay? So this was how you set up the physical characteristics of your watershed and select the correct methodology for your watershed. Now we are going to move forward and define different parameters of the methods that we selected. Remember, for the loss method, we selected SCS curve number method, and for transfer method, we have selected SCS unit hydrograph method. So we need to give these methods the parameters that they need. Let's click on one of the subbasins to show you how we can do that. So when you select the subbasin, there are multiple tabs over here. The first tab is subbasin that we have already selected the methodologies that we want to. The second tab is loss, and we need to select the parameters that we need for the parameters that we want to define for that specific subbasin 1, okay? Because the loss method is SCS curve number method, it is normal for the method to ask for curve number, which I know for subbasin 1 is equal to 74. You might ask, how do I know this? Well, I have done land use and soil texture analysis in ArcGIS before, and I have figured out the curve number specifically for this area, and this number is coming from prior analysis that I have done. If you don't know how to do this sort of analysis, I am going to link a video in the description over here and in my website. You can take a look at that. There are a couple of videos, actually 3 videos. One talks about how to download and process soil type. The second one talks about how to download and process land use data. And the third one talks about how to incorporate land use and soil type together to create curve number for your desired subbasin. One thing that I forgot to tell you, if you're interested to learn about the theory of SCS curve number method and also your transfer method, which is SCS unit hydrograph method, I have videos linked in my website in the description of this video that you can watch to familiarize yourself with the theory of these methods as well. Okay. The other thing that you must input for the loss method, SCS curve number, is the percent directly connected impervious areas. What does that mean? That means that if you are working in urban areas and there are some paved surfaces, impervious surfaces that are directly connected to your outlet, you should input the percentage of that right over here. Because these areas that I'm working on are mostly urban or are mostly rural areas, I don't have any directly connected impervious area, so I'm going to keep it as 0. And the last point that is very important is initial abstraction. Initial abstraction is a summation of water that is collected in depression storage, that is collected in canopy storage, and that is collected because of the initial infiltration. All these components are before surface runoff or overland flow starts generating, okay? Here, you need to input that in inches. How do you calculate that? I am sure that you know that curve number is connected to a parameter called capital S, and capital S is potential watershed storage. Normally, when SCS curve number was proposed, it was assumed that 20% of your potential watershed storage is going to be initial abstraction. This 20% is a good number for rural areas. For urban areas, it's been suggested that 5% is a better representation. If you want to change that, something that is not 20%, if I hover over it, you can see that by default, it's going to be 0.2%, 0.2 times potential retention. That means 20% of potential retention. If you want to change that, you need to calculate that in inches and input it over here. Again, for me, because this is a rural area, 20% is a good estimate. So I'm going to keep that as 20%. Okay, so I'm going to save this. Now the cool thing is, right now I input this for subbasin 1, right? Now if I click on subbasin 2, it automatically is going to go to the loss tab, and I can input the curve number for subbasin 2 as well. So take a look at that. I'm going to click on S2, and it automatically is on the tab that I need to input my curve number, and the curve number for The second subbasin is 75. I'm going to save it and click on the third subbasin, and the curve number for the third subbasin is again 75. Okay. All right, so this is how you input the information related to loss method. Similarly, you need to input some information for your transfer method as well. Transfer method is the unit hydrograph method, and the unit hydrograph method was based on SCS unit hydrograph that only asks us to input lag time. Lag time, again, is the time that it takes for the hydrograph to be moved. Okay, if you want to learn more about the SCS unit hydrograph, again, the video is going to be in the description and in the website as well. But how do we calculate this lag time? You might have heard this familiar equation of lag time is equal to 0.6 times time of concentration. And then once you calculate time of concentration, 60% of that would be your lag time. There's another way of doing that. If you are calculating lag time using SCS curve number method, you can use the same curve number to calculate lag time based on the length of your longest length to the edges of the subbasin and the slope, average slope of the watershed. You can calculate lag time as well. I'm going to show you the equation in a second. All right, this is the equation that I'm talking about. You have two options. You can use curve number to calculate lag time, or you can calculate S. And S is the potential retention that is calculated based on curve number. One thing that I want to mention, these two equations have the SI units. If you want to use the US customary system of units, you need to change the units of length to feet, and you need to change the units of S in inches, okay? And the unit of slope, or S naught, is percent. Also, if you're using US customary system of units, this number needs to be converted to 5.263 times 10 to the power negative 4. And this number, 25.4, should be 1. Also, if you want to correct me over here, this should be 25.4, not 25.1. All right, so I have used this equation, this top equation that has curve number, based on the curve numbers of the subbasin that I have, and I have figured out the value of lag time. Notice that lag time is in hours, but in HEC-HMS, lag time is in minutes. So you need to convert the values of lag time from hours to minute and put them in HEC-HMS. I'm going to go back and show you how you can input those numbers. All right, so we need to input the lag time over here. Let's start from subbasin number 1. Lag time for subbasin number 1, I calculated using the equation that I showed you to be 130. And then for subbasin 2, based on the equation, was 120. And I am rounding them up and down depending on which one is the closest number. And for the last one, subbasin 3, is going to be 113. Okay, so I'm going to save that. Now you're going to ask me, what is this graph type over here? And if you expand that, you will see that there are multiple options for the graph type. And what is PRF? Okay, so if you're familiar with the theory of SCS unit hydrograph, you know that there is a factor called peaking factor. And that peaking factor controls how peak of the hydrograph is going to be higher or lower. Essentially, it controls the hydrograph attenuation, how peak is going to change. This peaking factor, or C in the original equation, changes from 100 all the way to 600. When this method was developed, the original and the standard peaking factor was 484. However, for the most of practical application, the peaking factor of 284 is used. It is a good practice to do some research on the projects that have been done in your study area to see if there is a peaking factor from 100 all the way to 600 that you want to select for your study area. For my study area, I'm going to go with the standard method, and I'm going to select 484 as the peaking factor, which is the default version as well. So if I go to subbasin 2, you can see that's the number, that's the default standard choice for your subbasin. Okay, so we defined the loss method and transform method for all of our sub-watershed. Now, let's go back to, I clicked on subbasin 1 and I'm going to go back to subbasin. If you have any other method included over here, then there will be a tab opened up. For example, if I'm going to include a very simple energy budget or temperature index snow melt simulation, I'm going to say yes. You can see that there is a snow tab added over here in which I need to add different variables and different parameters over here to be able to simulate snow as well. But in this simple example, I'm not going to include any snow method over here. Okay, now we have defined all the methodologies and all the characteristics of different subbasins and how we want them to be modeled. The next step is to define the forcing variable of our hydrologic model. That is going to be rainfall. In this simple example, I'm going to define a hypothetical design rainfall of 50 year. So I have gone to NOAA Atlas 14 and I have noted down the amount of 50-year rainfall in my study area, and that's one number in inches. I'm going to use that one number in inches and create a rainfall distribution over time and input that into the model. How do I do that? Again, you need to go under components, and we are going to add some kind of weather-related variable over here. So when you click on the Meteorologic Model Manager, I'm going to create a new one, and I'm going to call it METS because this is a 50-year return period. I'm going to write METS 50 year and then create. You can see that the model is created right over here. Okay, when you click on it, it asks you all different weather and climates inputs that you want to input into your model. Obviously, if you have data for pressure, dew point, wind speed, temperature, you can add all that data. But this example is a simple design hydrologic modeling. That means that the only thing that I need to input is precipitation or rainfall. There are different ways to input your precipitation. If you have a gauge in your study area, you can input the gauge numbers over time, and that will be pretty easy. Remember that I want to do a specific hypothetical rainfall or hypothetical storm event. So when you click on this hypothetical storm and then yes, then you need to connect the basin that you want this hypothetical storm to be used for. What do I mean by that? So take a look at this tab. When you click on basins, it tells you that right now your basin is not connected to your rainfall. What we want to do is we want to connect our basin to the rainfall that we just created. Now you're going to ask me, what is the value of that rainfall? So once you created this hypothetical storm, there will be a hypothetical storm tab over here connected for all of your subbasin. Let's click on this hypothetical storm, and it gives you some options, some methodologies for creating this hypothetical storm. The hypothetical storm that I want to create is a design storm. And I know based on the SCS rainfall types that this watershed, this basin, is located in the area that is characterized by SCS type 2. So I'm going to click on that, and it asks me what is the depth of the rainfall in your study area. I have figured this depth from NOAA Atlas 14. I'm going to show you actually how to do that in a video that is linked in the description and also in my website. So if you don't know how to download this depth for your study area, this video that I'm going to post under description is going to be something that you find interesting. Okay, so I know that 3 inches is the number that I have. I want to have a uniform rainfall for the entire, for all of subbasin, for the entire basin. So I'm not going to change the area reduction or the spatial distribution over here. So I'm going to save this. All right. Now, you're going to ask, what is SCS type 2? In a second, I'm going to go to the HEC-HMS website and I show you what that is. As you can see, I am in the HEC-HMS technical reference manual under SCS storms, and it gives you an overview of what SCS storms are. So I'm going to scroll down. There is a map. Let me click on it. This map tells you that depending on which state you are in the US, what type of storm you need to be looking at. And this will help you to create that distribution of storm over time. Minnesota is in type 2. That's why I selected SCS type 2. And so what is the significance of this? So remember that I have 3 inches of rainfall. That's the depth. But I want that to be converted to a hyetograph. Hyetograph is rainfall over time. So this graph for different types will help me to convert, or help the model HEC-HMS to convert the depth of rainfall to distribution over time, 24-hour rainfall. Okay, so that 3 inches will be distributed over over a day, or 24 hours in a day, and it will give me a distribution or rainfall hyetograph. That's why I use SCS Storm, and specifically type 2. I link this website below, so if you want to take a look at it and learn more, you have access to it. The last step that we need to do to set up our model is going to be creating a control unit. The main purpose of a control unit is to define the simulation period and the simulation time step to generate your outlet hydrograph. So in order to do that, I'm going to again go under Components, and then you can see that there is a Control Specifications Manager, and I'm going to add that because if you're going to have multiple control units, in other words, if you're going to have multiple time periods that you want to have simulations, or if you want to have time periods with multiple intervals, hydrograph intervals, you need to have them numbered. Since I'm going to have only one, I just call that control and then create and then close this. You can see that there is a control. Let me actually, there we go, so it's more clear. There is a control specifications popping out. If I select that, it gives me some options to put over here. So start date, I am going to say 1st of June 2023. One thing that you need to pay attention, month should be in letters. So day is in numbers, 01, month is letters, and then year in numbers as well. Start time, beginning of the day, I'm going to say. And then the end date, I'm going to say, let's say 3rd of June 2023. And the end time, 0000. Time interval. So you need to select the time interval. This is the time interval that your hydrograph will be in. So if the time interval right now by default is 15 minutes, this means that you are going to have hydrograph points every 15 minutes. Okay. One thing that you need to pay attention is that your time interval should be less than the lag time for different subbasins. So let's say if your lag time for subbasin 1 is 10 minutes, your time interval should definitely be less than 10 minutes. This helps with the calculation and computation stabilizations in the model as well. So for me, because the lag time for my subbasins are pretty large, they're 100 minutes, larger than 100 minutes, 15 minutes sounds good for now. And then you can change that later if you want to have 30 minutes, 1 hour, so on and so forth. So I'm going to keep it 15 minutes for now and then save. All right. So this is all you need to do to set up your model. Now, the next step is to compute and to calculate the results. In order to do that, you need to go under Compute tab and to create a compute. So I'm going to create a compute and a simulation run, and it tells me, do you want to name this run? This will help you for different scenarios. Let's say that you have a scenario with one control and you have another scenario with another gauge, for example. Having multiple runs will help you to manage your scenarios. Right now, I'm going to call it run 1, and then next, it tells you, it asks you which basin you want to have. Right now, I only have one basin, but if you have multiple basins, you can select that. Next, your weather data. Next is your control unit, and eventually when you finish that, if you change your tab in compute, you can see that there is run 1 created for you. Okay, so we are going to use this specifications and run the model. So select it, right click on it and then click compute, and it will take a couple of seconds to create that for you. Okay, now you can see it's a good actually practice. I got 2 errors. Error number 1 is that the lag is not set for reach number 1, and that's correct. I totally forgot to have a lag time for the hydrograph that is generated in junction 1 and goes to the sink. Okay, and this essentially, I think if I fix this error, the second error is going to be fixed as well. So I'm going to close this and go back to my components, go back to basin, and then for reach number 1, click on reach number 1, and you can see the method is lagged, but I need to go to routing and input this lag number over here as well. This lag number, I know based on experience on this watershed that is going to be 120 minutes. If you don't know this, there are equations that allows you to calculate the lag number for the streams based on different characteristics of the river. Okay, and then save that. Okay, now let's try that again. I'm going to go under compute, right click and compute. You can see that successfully without any errors or warnings, the model was run. Okay, eventually we want to take a look at the results. So I'm going to click on the results tab over here, expand simulation runs, click on run 1. You can see that the results will show up. So the first one is global summary. Global summary, let me click on it and bring it over here. It gives you a very broad and high-level summary of your subbasins. For example, some good information is going to be the peak discharge or the maximum discharge in different subbasins, and the volume of water, and the time of the peak for each subbasin. If you click on each subbasin, it can give you a lot of good information about that. For example, if I click on graph under subbasin 1, it gives me the graph, the hyetograph, and also the hydrograph of this subbasin. Let me expand it a little bit. You can see that this top one is the depth versus time of rainfall, and this is my hydrograph. It shows the distribution of flow over time over the simulation period that I have. Okay, and then if you want to have the detailed or summary table of this result, I'm going to click on summary table. This will give you the detailed version of every 15 minutes of precipitation, loss, excess, direct flow, and total flow. Base flow is 0 because we defined no groundwater flow. And this would be helpful if you want to import it in Excel and essentially visualize it in Excel or any other visualization too. Other things that you can have, if you click on outflow, it will give you your hydrograph. Precipitation will give you the rainfall. Remember that our precipitation was 3 inches, but then we used SCS type 2 to distribute that precipitation over time. Cumulative precipitation, soil infiltration, so on and so forth. And you can have that for every other subbasin as well. And then in addition to that, if you click on the junction, you can have a graph, a hydrograph of that specific junction that you have. So the solid line gives you the hydrograph for that junction. The other 2 dashed lines are hydrographs from subbasin 1 and subbasin 2. And essentially and eventually, if you want to take a look at the hydrograph at the outlet, you're going to click on this sink and take a look at the hydrograph, the combined hydrograph for the 3 subbasins. Okay, so you can see that one of these hydrographs is coming from reach 1. So the dashed line over here is the outflow. The solid line is at the outlet. The long dashed line is from reach 1, and the short dashed line is from subbasin 3 that you can see. Okay, so in this video, I showed you how to set up and run a very simple hydrologic model in HEC-HMS using a hypothetical 50-year rainfall. There is a lot more things that I can talk about in hydrologic modeling, including continuous simulations. But I think this video will give you the background, the fundamentals of how to run HEC-HMS model. Let me know in the comment section what other sort of videos you want me to create on HEC-HMS, and how should I continue this playlist of HEC-HMS tutorials. The resources for this video, including the data and all the videos that I told you are linked in the description section of video. And if you are coming to this video from our website or LinkedIn, you can find all these resources in my website as well. Perfect. All right. Again, let me know in the comment what other source of HEC-HMS tutorials you want to see in this playlist.